this planet orbits a dead star. Long ago, that star resembled our sun. Then, near the end of its life, it swelled into a red giant. If the planet had been this close back then, it should have been destroyed. But if it once orbited farther away, how did it end up here? This is WD 1856b. About 80 light-years from Earth, in the constellation Draco, a faint white dwarf sits in the darkness. In 2020, astronomers studying data from NASA's TESS and Spitzer space telescopes noticed something extraordinary passing in front of it. The planet was roughly the size of Jupiter, but the star it orbited was only about the size of Earth. From one edge to the other, the planet was nearly 7 times wider than its host star, and it was moving astonishingly fast. Every 34 hours, WD 1856b completed another full orbit, passing less than 3 million kilometers from the white dwarf. Because the star is so small, each transit blocks more than half of its light, an enormous eclipse by exoplanet standards. At first, the discovery appeared to reveal a giant planet in an unlikely place. But its remarkably tight orbit soon exposed a much deeper problem. The problem begins with the star itself. A white dwarf is the dense remnant left behind when a sun-like star reaches the end of its life. First, the star swells into a red giant, expanding to many times its original size. Its enormous outer atmosphere can engulf and destroy nearby worlds. Later, the star releases those outer layers into space, leaving only its exposed core, a white dwarf roughly the size of Earth. At its present distance, WD 1856b would have been deep inside the red giant's atmosphere. Under normal circumstances, the intense heat and resistance should have destroyed it. And yet, the planet is still here. Either it somehow survived being swallowed by its dying star, or it was never this close during the red giant phase. If it once orbited safely in the outer system, then something must have sent it inward, across an immense distance, until it settled into the remarkably tight orbit we see today. But how could a giant planet travel so far inward without being destroyed? The white dwarf is not alone. It belongs to a triple star system, accompanied by 2 distant red dwarf stars. Over billions of years, the gravity of these companions may have slowly disturbed the orbit of WD 1856b. Instead of continuing along a calm, nearly circular path in the outer system, the planet may have been pushed onto a long, highly stretched orbit. Each journey around the system would then bring it extremely close to the white dwarf. During these close approaches, powerful tidal forces would pull and deform the planet. Orbital energy would be converted into heat, gradually shrinking and circularizing its path. Eventually, the planet could have settled into the tight, 34-hour orbit we observe today. This scenario would explain how the planet survived the red giant phase. It remained safely far away and only moved inward much later. But another possibility remained. Perhaps the planet was engulfed by the dying star and somehow survived inside it. To distinguish between these 2 extraordinary histories, astronomers needed a clue that could reveal when the planet had been heated. For years, both possibilities remained open. Then, the James Webb Space Telescope watched WD 1856b pass in front of its tiny star. Webb measured the planet's mass at somewhere between 4 and 11 times that of Jupiter. But an even more important clue was hidden in its heat. The planet's temperature was about 126 degrees Celsius, far warmer than expected. The white dwarf is too faint to heat the planet to this temperature, and no known source is producing that energy today. This means the warmth must be left over from an earlier event. Using models of how massive gas planets cool over time, researchers traced that heat backward through the planet's history. Their results suggest that the heating occurred between 3 and 5.5 billion years after the star had already become a white dwarf, far too late to have been caused by the red giant phase. This strongly supports a later inward migration. As the planet moved closer, powerful tidal forces from the white dwarf converted orbital energy into heat. WD 1856b has been cooling ever since, still carrying a fading thermal record of its mysterious journey inward. Webb discovered more than the planet's heat. As light from the white dwarf passed through the atmosphere of WD 1856b, it revealed signs of tiny cloud particles and hydrocarbons, most likely methane. This was the first atmosphere ever detected on a planet transiting a dead star. Webb has already observed 4 additional transits, which may reveal even more about the planet's hidden chemistry. But the importance of this system reaches far beyond a single distant world. In approximately 5 billion years, our own sun will expand into a red giant. Mercury and Venus will be destroyed, and Earth may share the same fate. Eventually, the sun will leave behind a white dwarf much like the one in this system. What happens to the outer planets, especially Jupiter and Saturn, remains uncertain. WD 1856b offers a glimpse of one possible future. It does not show us exactly how our solar system will end, but it proves that the death of a star does not always mean the end of every world around it. Long after a star's ordinary life is over, its planets may continue their journeys through the darkness.